Okay, so when you have a beautiful result that you've proved, I think what you should do is prove it again in a different way, and then maybe you'll get to understand it more, and maybe you'll get to know more interesting things about it. And so that's what I want to do with the volume of the permutahedron. It's not exactly going to be a new proof, but it's going to be a new way to understand what's going on. So it's going to be another explanation for the fact that the volume of the permutahedron is n to the n minus 2. And this is going to be so what I want to tell you about today is about zonotopes. Have I mentioned zonotopes in this class? No? I wasn't sure. I don't remember mentioning them. So here's the definition. A zonotope is a Minkowski sum of segments. Okay. Do any of you happen to have a new marker by any chance? Yeah? I'll give you one back. I have like 30 in my office, but thank you. I just need this one. I'm just supposed to use a new one each time because it doesn't show otherwise on the video. So a zonotope is a Minkowski sum of segments. I'm sorry? A one-dimensional segment. Yeah. So yeah, just that. So example, you could have a vertical segment plus a horizontal segment plus a diagonal segment plus a more diagonal segment. Okay. And let's do this in 2 dimensions, but this could be in any dimension, right? And so then when you do this, if you do it carefully, you're going to find that this looks like this. Can you see down here? Maybe not. So it looks something like that. Okay? That's a zonotope. So it's a simple definition. Okay? And of course, I'm skipping the process, but you know how to do a Minkowski sum. You have to go through this whole process. Now remember, actually, one thing that I should remind you, one way of getting the Minkowski sum of a bunch of segments is to do something like this. For example, you take this vertex plus this vertex plus this vertex plus this vertex, and you add them, and that gives you a point. And then you choose maybe this vertex, and then this vertex, and then this vertex, and then this vertex. And then you plot it, and you find a point. And you do that for every possible choice of a vertex of each polytope, and then you're going to get a bunch of points. Some are going to be vertices, some are not, but then all of them are going to be. The convex hull of all those things is the zonotope. Okay, we discussed this. And another example is the permutahedron, which we proved was the Minkowski sum of the segments delta ij for all I and j between 1 and n. Okay? And delta ij was just the segment joining the unit vector ei and the unit vector ej. Okay? So those are some examples of zonotopes. Okay. So here's a nice proposition. The zonotope let's call it Z, and it's the Minkowski sum of segments V1 up to Vn in Rd. This zonotope can be tiled by parallelepipeds, can be tiled with the parallelepipeds what you're going to do basically is you're going to look at every d tuple of these guys, let's say vi1 up to vid. Let me ask you guys something. Are you getting confused by the notation and thinking that these are vectors and not segments? So keep in mind that each one of these things it's a segment, not a vector. So when I write this, I don't mean that it's a sum of vectors. I mean that it's a Minkowski sum of segments. And that's what I mean here also. Okay. Tile with the parallelepipeds like this. Okay. And if you look at what, well, let me continue. Let me complete my sentence first. For 1 for each basis vi1 up to vid of r to the d. Okay. So you're going to look at your m vectors, and you're going to see which d tuples of them form a basis for Rd. Now, if you have d vectors, then they're going to be a basis even only if they're independent. So I could have just said 1 for each independent set. Okay. And if you take d vectors, and if you take d vectors that are linearly dependent, and you look at the Minkowski sum of their segments, then that's exactly going to be the fundamental parallelepiped generated by those things. Okay. So this you should think of as being something like, you know, these are vi1 up to vid, and then it's just this parallelepiped. Right? Okay. So let's do an example to make sure that this is clear. What is it that I'm saying here? Let's do the example of the permutahedron pi3, which is delta 1, 2 plus delta 1, 3 plus delta 2, 3. Okay? And let me draw these segments. So these are just the coordinate axes. And then this is going to be 1, 2 plus 1, 3 plus 2, 3. Okay? And so we know already what this looks like. This is a hexagon, right? It's a regular hexagon. Okay? 1, 2, 1, 3, and 2, 3. So what is this proposition or this theorem telling us? It's saying, look at your collection of vectors and look at all the possible bases that you could form with them. Okay? And now I run into the annoying problem that these are not really bases because I live in a dimension smaller. Okay? So maybe let's just say one for each independent set. Independent set. Okay. So you're going to look at the vectors 1, 2, 1, 3, and 2, 3. And as a triple, they are dependent because the vector 1, 2 plus the vector 2, 3 plus the vector 3, 1 equals 0. Okay. So then you take 1, 2, and 1, 3, and you make a parallelepiped out of them. Okay. So that looks like this. 1, 2 plus 1, 3. Then 1, 2, and 2, 3 gives you this tile. 1, 2, and 2, 3. And then 1, 3, and 2, 3 gives you this tile. Okay, this is 2, 3, and this is 1, 3. And so the statement says that this is a puzzle that has a solution. You can take these three guys and tile that puzzle. Okay. And that's not very hard here, of course. But the fact is that you can always do this. Okay. So that's pretty cool, I think. I like that. Okay, that's the example. Any questions about this example or what this statement is saying? Okay. So I'm going to give you a sketch of a proof, but you'll notice that I'm even putting sketch in quotation marks. So this is not that close to a proof, but at least it gives you an idea. And I'm even going to be more vague and say just induct. Okay. But what do I mean by this? Well, just imagine that you're putting in another summand into this picture. Okay? Maybe they say that a picture is worth 1,000 words, so that's exactly what I'm going to do. So this is let's say the inductive hypothesis. So let's say that you already managed to prove the result for these three summands, and now you're going to add an additional summand, like maybe, I don't know. Imagine that you put plus and then a vertical segment. Okay? So what does the zonotope look like? Well, I need to take this zonotope and add the red segment. Okay? And so you notice what that looks like then is I'm going to get something like this. So you just get this right here. Okay? And then the point is that it's almost like you see already what you're supposed to do. You're supposed to go like this. Okay? And the new part of the zonotope that you added very naturally decomposes into, you see this cell is 1, 3 plus the new guy. This cell is 1, 2 plus the new guy. And this cell is 2, 3 plus the new guy. And so what you get is a nice belt that is basically, it kind of tiles itself. Okay? But lots of quotation marks here. Okay? Because I think actually you can easily make this into a proof for 2 dimensions, but you realize that things get a lot muddier in more dimensions. Okay? And the same thing works, but there's a lot to say here. Okay? But the point is that this is the old part, and you know how to tile it. And the new part tiles into the new cells. Okay? So that's a very rough sketch of the proof. But to really make sense of this, to really make this precise, we basically need to understand all of these things better. We need to understand zonotopes better. We need to better understand zonotopes. And that is very naturally going to give rise to understanding hyperplane arrangements. And if you want to understand hyperplane arrangements, then you very naturally run into the notion of matroids. Okay, so these are some words that probably you've heard in your life. You might know vaguely what they mean, and they're going to be the subject of the rest of the class, basically. So, I mean, it's not that the rest of the class is going to be about proving this result, but it gives me a good excuse and a good motivation to go into these topics, which are going to occupy us for the rest of the semester. Okay. Now, one thing that you should notice here is that there's a simple corollary here. Since we're talking about volumes, this basically tells you how to compute the volume of a zonotope, right? Because the volume of the zonotope is going to be equal to the volume of all the different cells of this tiling. Okay? And so that's a sum over VI1 up to VID independent of the volume of that parallelepiped. But parallelepipeds are the easiest thing to compute the volume of. We discussed that all you have to do is take the determinant of those vectors. Okay? So, and take the absolute value so that it's a positive number. So, determinant of VI1 up to VID. Okay? Now, one thing that you might notice is that I actually don't even need to require these to be independent, because if these vectors are dependent, then the determinant is 0. Right? So, but anyway, I mean, it's a shorter formula if you know that to begin with you only care about the independent ones. Okay? Now, if you look at what it is that I mean, what this statement has to say about this problem of the Bernoulli-Hedron. But one thing you'll notice is that we're expressing the volume as a sum of a bunch of different things. Okay? One for each independent set. Now, if you look at what the independent sets are here, they are, and let me be suggestive in how I draw them, 1, 2, and 1, 3. Then this is 1, 2, and 2, 3. And this is 1, 3, and 2, 3. My point is that these are precisely the 3 spanning trees of the complete graph. And that's what's going to happen for any Bernoulli-Hedron. For any Bernoulli-Hedron, if you have a Bernoulli-Hedron, then the independent sets correspond to spanning trees of Kn. And the other thing that you notice is that each one of these things has unit volume, and that also happens in general. Okay? Each one of these determinants is 1. And so then what this tells you is that you have decomposed your permutohedron into little boxes of volume 1, and the number of boxes is the number of spanning trees. Okay? So that gives you another conceptual explanation of why this formula is correct. Okay? You might have heard the word unimodular. And that word unimodular applies here. So a bunch of vectors are unimodular if all of these determinants are 1, 0, or -1. Okay. Okay. So let's talk a little bit more about zonotopes then. They look pretty cool. I mean, they look pretty cool because the pictures look pretty cool, but I don't know about this definition. This definition is maybe a little bit strange, and it's going to turn out that these objects are equivalent to hyperplane arrangements. Okay, and somehow the theory of zonotopes and the theory of hyperplane arrangements are more or less equivalent to each other, and that's what I want to describe next. So these are basically these are more or less equivalent to the following things. A hyperplane arrangement let's call it script A. That consists of H1 up to Hn in Rd. It's just a collection of hyperplanes. It's a collection of hyperplanes where each hyperplane Hi, of course, is given by one linear equation. Right? So x is in Rd such that let's say x dot bi equals 0. Okay. So vi is the normal vector, and then that's your hyperplane. The things that are orthogonal to that vi. Again, if you're paying attention to the subtlety between a space and its dual space, then you'll realize that if my vectors live in R to the D, then really these things live in R to the D dual, because I'm thinking of this as a linear function on VI. Okay. Okay. That's not going to be too important for us. So then the next thing, well, so maybe let's just draw a couple of examples. Yeah.
For your definition correctly, the origin will all be vector.
That's a very good point. So you notice that I define my hyperplanes to all have right-hand side 0. So they all go through the origin. Okay. Sometimes people want to consider what you might call an affine hyperplane arrangement, where the hyperplanes don't have to go to the origin. Okay, and so in the literature, sometimes when people write hyperplane arrangement, they mean this, and sometimes they mean that it's shifted. And it's something good to keep in mind whenever you read papers about this, that they might mean one thing or the other. The theories are very similar, of course, but for me, for now, it's going to be they're all going to go through the origin. And by assuming that, I make the job of drawing pictures a little bit harder on myself, but that's okay. So let me show you. It's hard to draw examples, but here's an example. I mean, it's hard to draw examples that are kind of interesting. But this is what a hyperplane arrangement might look like in R3. Okay. And we could even add a hyperplane here. Okay, but of course these hyperplanes continue, right? And this is the origin, and all the hyperplanes go through there. So that's one example. Another example. Let me try to draw this carefully. Oh, I didn't want to erase this picture that I had here. Okay. Well, then maybe I'm going to change my plan. Instead, let me draw this hyperplane arrangement. Okay, so this is a hyperplane arrangement in a two-dimensional space. Okay, and here let me draw the normal vectors. Okay, so here's one of them. Here's another one. And here's another one. Okay. And so this is going to be, in the notation that I had here, this is going to be V1, V2, and V3. Okay. And you'll notice that for V1 I have a choice. I could point it this way or this way, but that's fine. Now, why are these more or less equivalent to each other? Because of the following. What happens if you take the Minkowski sum of V1, V2, and V3? Well, I tried to do it to match that picture. Okay, so these directions are precisely these three directions, and so if you draw the zonotope Z equals V1 plus V2 plus V3, okay, then this is V1, this is V2, this is V3, and hopefully you can see that these pictures are a little bit, you can kind of think of them as being dual to each other, and you're going to see that even more if you decide to overlay the two pictures. Okay, which, again, if you're being strict about what's in one space and what's in the dual space, then this picture is in one space and this picture is in the dual space, so you don't really get to put them on top of each other for free. But I'm going to do it anyway. You can have a map that identifies these two dual spaces with each other, and then when you put this thing on top, then you get this very nice situation where every vertex there lines up nicely with every region here, and so on. Okay. And that's the sense in which these two. I mean, that's what I want to get to. I want to explain to you what precisely that picture means and why that says that these two are more or less equivalent to each other. Okay. So I don't think I need any of this. So we need a bunch of definitions. I forget, have I defined fans? Okay, so let's define a fan. A fan, it's simple. It's precisely a polyhedral complex where all the polyhedra are cones. So remember, a polyhedral complex is just a bunch of polyhedra that are glued together face to face. And if everything in there is a cone, then it's called a fan. Okay? So a fan is a polyhedral complex made of cones. Okay, so where each Ci is a cone. Okay. Now, can you see why this is called a fan? The thing is that in the US, fans are in the ceiling and they rotate, but generally. But if you think about before that, the fan is like a fan that high society ladies would fan themselves with, you know, very elegantly. That's what you should be thinking of. It's like a. Let me see if I can draw a fan. So it's something like this. It's like this, right? So that's my best picture of a fan. But each one of these things is a cone, and so that means that we're really supposed to have a vertex. So it's not exactly a fan. And these things keep going. They don't stop. They go off to infinity. But the point is that each one of these little flaps is polyhedral, and they're glued face to face. So that's why these things have the name fan. So actually, so the ceiling fans are also fans. It's like this, right? So, I mean, it's not exactly a ceiling fan, but this is also a fan. Okay? Because I'm taking 3 cones and I'm gluing them at faces, not at facets, but that's fine because as long as the intersection of any 2 cones is a face of both, which it is, then that's okay. So those are 2 examples of fans. A fan is complete. So we're going to say that, and I should say this is in let's say RD. Okay? And we're going to say that this fan is complete if it covers the whole space. Okay, so neither one of these things is complete. A complete fan is something like this. Okay. The plane divided into its 4 quadrants. Okay, that's a fan. That's a fan. Because each one of the pieces is a cone, and they intersect nicely, and it's a complete fan because it covers the whole plane. Okay. Now, another example of a fan is something like this. Because remember that it's a little bit counterintuitive, but we call this a cone. It's not a pointed cone, but it's a cone. Remember we said cones are pointed if they had a point, but this is a cone because a cone because it's close under taking positive multiples, and positive combinations. And so this is a fan, but it's kind of a strange fan. So we say that F is pointed if the origin is a cone. Okay. Okay, that's the definition, but I think it's clearer to just call it pointed. It's pointed if it's pointed, right? It's pointed if it has a point, And that point has to be the origin, because our cones are centered at the origin. Question? So this one is not, this one is not, this one is, and this one is. Yeah.
The last one, 0 is in there.
You see, 0 is covered, but 0 is not a cone of the polyhedral complex. Remember what this means. A polyhedral complex is a set of cones. And so in this case, the cones are the upper plane, the lower plane, and their intersection is the line. Those are the 3 cones in this picture. And the point is not one of those cones. Whereas here, the point is one of the cones. It's just the 0 cone. But that's what I mean. This is more confusing than enlightening. You understand what it means to be pointed, and you're correct. It is what you think it is. Okay. So with that, so here's a nice gallery of examples, but let's talk about some more interesting examples. Okay. So another and a very important example is, let's say that you have a hyperplane arrangement, like this one, okay, or like this one. Then, if you look at it, it's a fan. Just this is the origin, and then the cones are what they are, what they look like they are. Okay. So if you have a hyperplane arrangement in RD, how can we say mathematically what I just said? Well, we're going to define a face of the arrangement. So the faces of the arrangement are given by the following thing. Let me erase this zonotope because it's distracting. I mean, it doesn't live in this space anyway. So, for example, this region I want to call a face. And how can I describe it? I can describe it in terms of inequalities by saying that V3 dot my point is positive, right? I'm on the positive side of V3. I am on the negative side of V1, and I'm on the positive side of V2. Okay? So to specify a region, I just have to tell you for each hyperplane, am I positive or am I negative? That's how you specify a region, and so that's one way of specifying a face. Okay, so the set of points such that point x such that vi dot x is either bigger than 0 or less than 0. And you get to make that choice for each I. Okay? Choose for each hyperplane HI. Yeah?
Which has the right number of hyperplanes in order to actually make it a fan, though, right? So that if your lower example, if you took one of those hyperplanes away, you would have a pointed. Oh no, you have a pointed.
But you're right.
Yeah.
And this is an example of a hyperplane arrangement that has only one hyperplane.
Right.
And it gives you a fan, but it's not a pointed fan. Yeah. Now, let me tell you, I would also like to call this a face. So how can I describe that red thing? Well, it's kind of the same thing. I just have to say that according to V1, I'm actually on the hyperplane. So not only do you get to be on the positive side or on the negative side, you can also be on the hyperplane. Okay? So to specify the red thing, I have to say V1 dot my point is equal to 0. I'm on the hyperplane. Then I'm on the plus side of V2, and I'm on the plus side of V3. So you should choose not only whether you're bigger or smaller, but you can also be equal. Okay. And so a phase is given by such a description where you chose some signs. Okay, that's the definition of a phase. And then I define my fan to be the phases of the arrangement. Okay. And that is going to be a fan. Yep?
Your definition of fan, you need the CI, the intersection of all CIs to be non-empty. Is it possible to make a cone arrangement where you can have rectangles that don't intersect?
I think so. The question is, shouldn't these intersect in the same point? And the thing is that I said this, but I didn't write it. That the cones are centered at the origin, and I want them all to be centered at the origin. So let me write that. Actually, I didn't say when I first wrote it. I kind of just said it in passing. So it's a cone centered at the origin, and that's why I put the origin here. And so now your question answers itself because they all intersect at the origin at least. Okay. So we're going to call this the fan of the arrangement. Actually, one thing I should say is that I want those faces to be closed. I don't want them to be open because cones are closed. I mean, polyhedra are given by weak inequalities, right? And so I need to do that here also. So these should not be strict. These should be weak inequalities. Okay. So that's how you get a fan from the arrangement. But basically, I mean, you didn't need this definition. You can just look at it and you see that when you draw a hyperplane arrangement, there's one thing that's extremely important here, which is that these are real numbers that we're dealing with. This is a real vector space. And so when you have an equation, something dot x equals 0, that separates your space into two. A place where something dot x is bigger than 0, and a space where something dot x is less than 0. Okay? And then if you just see how those hyperplanes cut up your space, you call those the faces, and that's a fan. Okay? Okay, so that's a more interesting example. The fan of an arrangement. Let me show you another important example. Which is this. Suppose that P is a polytope in RD. Okay? Now, if F is a face, then I'm going to define the normal cone of F to be the following thing. It's the directions in RD dual. They're the directions such that the face F maximizes the linear function C. Okay? So for example, if this is P, okay, and let's say that this is my face F, then what I ask myself is, according to which linear functions is this maximum? Is this phase maximum? And that says basically you have to point in that direction. You have to point towards it, and you have some leeway, right? You can you can point here all the way here. Where should I stop? Basically, when you're perpendicular, then f is still maximal. And then as soon as you go past perpendicular, f is not maximal anymore. It's this one that becomes maximal. And the same this way. So f is maximal, f is maximal, f is maximal, f is maximal, until you're perpendicular. But then once you go past perpendicular, then this one becomes maximal. So that means that the normal cone looks like this, right? Okay. It's a very good question, and I worded this very carefully so that it would be closed. So I said the face f maximizes c, but it might not be the only thing that maximizes. So for example here, when this is vertical, then f maximizes, and these things also maximize, but that's fine. That's no reason to throw out this direction. Okay. So that's the cone normal to f. Normal cone to f. Okay. And the point is that as you do it over all the faces, you're going to get a fan. So the normal fan of P is what you get when you do this for all faces. Okay. So, for example, if G is this segment, then there's only one direction that gets maximized at all of G, and that's the vertical direction. So this right here is NG. For this face, it's this direction, and so on. For this vertex, it's this direction. I mean, you should be thinking that it looks kind of like this, basically. And I'm just kind of separating all the pieces. Okay. So that's the normal fan. Is that clear? This is kind of fun. I think for fun, you guys should draw a polygon and then draw the normal fan. I find it kind of amusing. Now, with this information, we can revisit this correspondence between hyperplane arrangements and zonotopes. Okay? Because what's the zonotope that we saw? It's I'll do it in blue. It looks like this. Okay. So then, what is the normal fan? It's do you see it? It looks like if you do this to this picture, what you get is this, which is the arrangement. Okay. And let's be more precise. I call these, I forget what order I labeled them in. So I call these 1, 2, 1, 3. Well, it doesn't really matter what I call them. Let's call them V1, V2, and V3. Okay. Then, if you notice, those are exactly the normals to the hyperplanes here. So this normal direction is V2. Well, almost exactly, because my picture is not that great, but if I did it well, then it would be exactly. And so now I can actually state what the correspondence is. So let's say that you have V1 up to Vn be a subset of Rd. So let Z be the Zonotope minkowski sum of these guys. Let A be the arrangement of hyperplanes V1 dot x equals 0 up to V1 Vn dot x equals 0. And then what I'm saying, so it's a proposition, by the way. I'm making a statement here that then the normal fan of the Zonotope is the arrangement. Okay. Now I cannot really say this. Why is it that I cannot say this? Because this is a fan, and this is a set of hyperplanes. So it's kind of like you want to say this, but it's not mathematically precise. And so really what I need to say is that this is the fan arrangement. And this is the one-to-one correspondence between Zonotopes and hyperplane arrangements. So what I'll do next time is I'll prove this statement for you, and then we'll see what mileage we can get from it. But I think the point that I want to make is that Zonotopes, I find Polytopes to be harder than hyperplane arrangements. So hyperplane arrangements are new, but you're going to find that they're easier. And so this tells you that for Zonotopes, actually, a lot of things are just a little bit easier because you can do it with the arrangement, which is a bit of an easier object. Okay. So just a couple of announcements. We have a seminar here right now, and I think it looks very interesting, actually. And then you know that there's homework due Friday.